So considering the premise of this course, a fair and logical place to start is simply what is fascia? When we think about fascia, the first thing that we want to think about is connective tissue. At the end of the day, that's all this is just a connective tissue system that is present throughout the body. A little bit more specifically, fascia is an epimuscular connective tissue that essentially spans the entire body and works to interconnect all of our different biological structures. So while we have our predominant construct of fascia as it relates to muscle tissue, it's important to understand that really fascia is integrated and interwoven throughout all of our biology, from vessels to nerve fibers to bone tissue to tendons and then to muscle. Fascia is predominantly made up of different types of collagen, proteoglycans, water, elastin fibers, and then some other material. Between the collagen fibers and the elastin fibers, the collagen is what gives fascia its fibrous nature and its tactile structure, where the elastin fibers are what provide the elasticity or the elastic function of fascial tissue. We should also understand that fascia is highly enriched in sensory motor bodies. So fascia plays a crucial role in body awareness through proprioception, mechanical stimulation through mechanoreceptors, and then it also plays a significant role in the pain process, or how we perceive pain through the nociceptive bodies that are found within fascial tissue. Collectively speaking, fascia is a dynamic and adaptive tissue. It's highly malleable. It has a very unique viscoelastic property to it, which allows it to be deformed at great rates and great lengths, and then still be able to return back to resting length without damage. Healthy fascia should have a distinct nonlinearity to it, but at the same time also has a very profound lattice-like structure to it. And depending on the type of fascia that we are discussing, the density and the distance and the layering of these fibers is different depending on the physiological demand or the biomechanical demand. So broadly speaking here, we can classify fascia as being one of two different types of fascia. We have superficial fascia, and then we have deep fascia. And these are very distinctly different types of connective tissue. The superficial fascia is what we see between the skin and the muscle and kind of interspersed in between the adipose tissue. This type of fascia is going to be very membranous. It's almost going to be greasy and watery. And we're going to see a lot of responsibility with regards to that sensory motor function. So superficial fascia does not do much for us in terms of movement. It does help to permit gliding between tissues and allow muscles to work in tandem or collectively. But really with superficial fascia, we're thinking more about the sensory motor function of fascia. The deep fascia, on the other hand, is going to be much more involved with mechanical action. So the deep fascia is going to be found more situated within muscle tissue, interconnecting muscle fibers, and then again thereafter enveloping around the muscle belly and helping to keep proximity and structural alignment, or congruency rather, between adjacent muscular compartments. Now, beyond the superficial and the deep fascia classifications, we can then take it one step further, and we have a little delineation within the deep fascia. Here we have two different types of fascia, the epimysial fascia and the aponeurotic fascia. The epimysial is going to speak more to that fascia that is enveloping the muscle fiber and enveloping the muscle bellies, whereas the aponeurotic fascia is going to speak more to the fascia that kind of broadens and extends off of the tendinous tissue. With this aponeurotic fascia, the thing we want to think about here for the sake of functional applications is the myofascial force expansion. So essentially the fascial tissue that is creating a broader tendinous sheath that is allowing us to transmit force across a broader surface area. No different than any other connective tissue structures that we see within the body between ligaments, tendons. We can think about fascia as adhering to Davis's law primarily. So with fascial tissue, and when we're thinking again about training and restoration applications, we want to think about fascia as being receptive to mechanical input, predominantly stimulated by eccentric loads. We want to think about the rate at which load or force is being applied. We want to think about the directionality in which force is being applied. And then we want to think about the general neurological demand or the complexity of movement. Because again, as we mentioned with the sensory motor acuity to fascial tissue, the more complex that movement becomes, we could argue that there's more of a fascial involvement as that complexity increases with movement demand. Finally, when we're thinking about what is fascia, we want to think about the 4 primary mechanical properties to fascia. These 4 properties are going to include viscosity, or the ability for tissue to glide, elasticity, the ability for the tissue to extend and then return to resting length, plasticity, or the ability for tissue to create stiffness and then be pliable within that stiffness. And then we have those sensory motor properties that we've covered already. Those 4 mechanical factors for fascia are what strength coaches and practitioners are going to predominantly be thinking about when we're thinking on exercise selection and programmatics and how we are organizing our training and our restoration with our athletes.